In this video, I would like to introduce Gauss's law. All right, so Gauss's law says the following. The total flux through a closed surface is proportional to the charge enclosed. Okay, so what do I mean by a closed surface? That means that there is a distinct inside and outside. So, like a bubble, you can't get into it without passing through the surface. If there's any opening at all, then it's not a closed surface. But if there's a clear inside and outside, then it is. Okay, and so that allows us to determine what is enclosed by the surface and what is not. Okay, so the way to express this law mathematically is to, first of all, write down the flux. So the flux through a closed surface, E dot dA. And to indicate specifically that it is a closed surface, we use this symbol. Okay, so it's just a regular integral sign with a circle to indicate that it's closed. Okay, and that is equal to the charge enclosed times some proportionality constant, which turns out to be 1 over epsilon naught. Okay, so let me talk specifically about those parts. So again, this indicates that it is an integral over a closed surface. It's not really necessary to include the little circle. It's just a reminder about that part of the rule. The E dot dA is the flux. And specifically, E dot dA is E times dA times cosine theta. Okay, so the angle matters here. It's important not to forget about that part. And then epsilon naught is the permittivity of free space. So we've seen this constant before. Okay, the place where we have seen it before is that K, the electrostatic constant that shows up in Coulomb's law, is 1 over 4 pi epsilon naught. And in some of the examples in this chapter, you'll see why we like to use epsilon naught in a lot of places rather than K. All right, so let me just quickly give a couple of examples where we can use Gauss's law to think about what's going on or to understand what it is saying. So first of all, let's say that we have a positive charge like this, and I'm going to draw some weird surface, just something kind of like this. Okay, there's not actually anything there. It's just a mathematical structure I've drawn. Okay, so we call this a Gaussian surface because we use it for Gauss's law, but it is totally imaginary. And so you should not think about it getting charges on it, having charge move around on it. It's not going to have any forces, nothing like that, because it's fake. It's not actually there. It's just a thing that I've drawn. Okay, so that's critical that you understand that this is just something I drew. You could draw a different one. Any Gaussian surface is perfectly fine, and Gauss's law applies to all of them. Okay, so with that out of the way, I have this Gaussian surface, and let me draw some electric field lines from my charge. Okay, and I won't bother drawing ones that don't intersect the surface, but you'd keep drawing them evenly all the way around. Okay, so essentially, for the Gaussian surface that I drew, there is no charge enclosed, because the surface only has the charge outside. Okay, so that's the only one that there is in this problem. And that means that there is no flux through the surface. Okay, so the total flux through the surface is 0. All right, so how does that make any sense? Well, I have in different spots, if I start drawing some area vectors, I can draw a dA vector out here, one over here, one kind of like this. Okay, and I expect that on this right-hand side, which I am outlining with a dotted line, there is going to be a positive flux because the electric field is pointing outward. The area vectors are pointing outward generally, and so overall that'll be positive. But then over here on the other side, I have my little area vectors pointing opposite the direction of the electric field. And so for this part, there's going to be negative flux. Okay, so the total flux has to be 0 by Gauss's law, and the way that works is that any field line that goes in has a little bit of negative flux at that point, but then it also goes out. Okay, so every field line that goes in also goes out. Okay. And since the area vectors are always outwards, which is just a convention, we're going to have negative flux where those field lines went in, positive flux where they go out. Okay, so that's the reason why we get that cancellation. There's no way to have more field lines going out than going in unless there's charge inside. Okay, so let's show an example like that. Okay, so let's say that I have now a positive charge that's inside my Gaussian surface. Okay, and again, I can draw any surface I want. And I'll draw some field lines going outwards. Aiming for evenly spaced, like this. And now we can see that there are lots of field lines that are going out that are not coming back in. And if I draw some area vectors at different points along the surface, I can see that I'm going to get a positive flux basically everywhere along the surface. Okay, so here I'm getting positive flux because I have positive charge enclosed. And here we have field lines go out without going back in. Okay, and even if I made little loop-de-loops in the surface, like let's say I changed this one so that it kind of looped back around like this instead, well, even for that case, we're still going to have that field line goes outward here, and then inward here and outward here. So for that field line, it still goes out more times than it goes in. So that's still going to contribute a positive flux altogether. All right, so that's what Gauss's law says. If I want more field lines to be going out, then I need to have more charge, more positive charge inside the surface. Okay, so that's the idea behind Gauss's law. It has a mathematical equation, as you saw, but usually it's not reasonable to try to use it for calculations. Okay, so the only times that we could do calculations for integral of E dot dA is if E dot dA equals E dA. So if E is parallel to A, or if E dot dA equals 0, which happens if E is perpendicular to A. So in those two cases, we can do calculations. Pretty much any other case is just much too complicated to be able to do an integral over the surface.